So make sure to put in your information for question number 2. But here's the scenario, very similar to what we're going to be doing in the lab today. It says a student is given an unknown metal and asked to find the heat capacity of the metal. She boils water and lets the metal boil for several minutes before transferring the hot metal to a calorimeter with room temperature water. The student records the following information. I mean, look at the lab benches, ladies and gentlemen. You have ring stands with a beaker of water sitting there ready to go. This is exactly what you're going to be doing in a little bit. You have your styrofoam cups, your calorimeters that you're eventually going to be putting stuff in. You have metal rings that are sitting on there as well. So this is basically what we're doing. Another good thing to note is look at the measurements that were needed. One of the issues that we have with students in their lab reports is they don't know what measurements always to make when we don't do these fill-in-the-blank labs. This lab that you're doing today is not a fill-in-the-blank lab. It's more of a, here's the scenario, figure it out, and now give us the purpose, materials, procedure, all that type of stuff. If you recall last class, we put ice in our calorimeter. And when we put ice in our calorimeter, the water cooled down because the water lost heat to the ice. We calculated how much water heat was lost. Well, if the water lost that heat, the ice gained that heat. There's a paragraph on the back side of that sheet of paper that was talking about the conservation of energy law. The energy is transferred from one thing to another. We can use that same rationale to solve a question like this. So what the student's trying to do is find the heat capacity of a metal. By the way, any pure element on the periodic table, we know the heat capacity for it. On the back side of your periodic table that we gave you, it actually tells you the heat capacity for these different elements. So you can almost identify an element by its heat capacity. What we will always want to do in any type of problem like this, try to keep my data showing there, is divide it into 2 parts. We want to figure out what's happening to the water. And if we know that, we can figure out what's happening with the metal. So how I approach this problem is I try to divide out the work. You are going back to the same equation that we have used a few times now. Q equals mc delta T. What I want to do, remember what this experiment is they're heating up metal. They're putting it in boiling water. You heat up metal long enough, then you put it in your styrofoam cup calorimeter that has some room temperature water in it, just like we did with the ice last time. That room temperature water is going to warm up. If it warms up, we can figure out how much heat did it gain. We can solve for the Q value. In order to know that Q value, we need to know the mass of the water. That's given to us right here, 123. Next, I need to know the C value for liquid water. Now again, this is on the top of your sheet of paper. It's the very first entry there. This is the 4.184 joules per gram degree Celsius. Change in temperature. Notice on the data collected on the top, the initial temperature of the water was 22.3 degrees Celsius. Again, that's roughly room temperature. The final temperature, after you put something hot in it, the water increased its temperature. That should make sense. You put something hot in water, water's going to gain that heat, it's going to get warmer. Final temperature is 35.7. So if I subtract those two, that gives me my delta T. What is that, 13.4? Right. If I multiply those 3 things, that will tell me how much heat, which the unit for heat is a joule, did the water gain. Now again, what we've told you is that with thermal math, especially because of the delta T and other issues, we're not as concerned about significant digits as we will be for other things throughout the year. So if you just go to the ones place, we'll accept that. Dorn, did you get a number to the ones place there?
Should I round up?
if you need to, because the number and after decimal.
I got 6,896.4.
6,896. I'm actually going to slightly change what I'm doing here. You don't have to erase that. You have a sheet of paper that's a little bit wider than my smartboard. If 6,896 joules is how much energy that the water gained, okay, you put something hot in water, the water heats up. We can figure out numerically how much heat did it gain. If that is how much the water gained, now I'll do my metal part. That must also be the amount that the metal lost. Conservation of energy. If one thing gains energy, another thing loses that same amount of energy. So what we're going to do is we're going back to Q equals MC delta T. I know my Q value already. It's what I just solved for up here. However, does the metal that starts off in boiling water, again, looking at your lab benches, ring stand with a water beaker in there, and we're putting metal in boiling water, and then we're putting it in a cup in room temperature. The water heated up. That's why we have a positive Q value. Is the metal going to heat up or cool down in the process of this experiment? Cool down, right? So it's not going to be a positive 6,896. It's a negative 6,896 joules. Equals the mass of the water. Well, the mass of the metal rings. That's given to me in the problem of 75 grams. What makes this calculation a little bit different is we are solving for the heat capacity. We're solving for the C value. So I don't have that number. So that's my variable. That's like my X. The number one issue with this question is knowing what to plug in for delta T. I'm going to go back up to our data for a second. I take metal, I put it in boiling water, and then I put it into a cup with room temperature water. What is the final temperature? So if we want to start off with final, what's the final temperature of the metal going to be? So room temperature? I mean, if we let it sit out for all day, I suppose it would get back to room temperature. It should be 35.7. Everything in that cup at some point is going to reach the same temperature. Remember, hot things are going to get a little colder, colder things are going to get a little hotter. There's going to be a balance that's reached over time. So, final temperature is 35.7. What's the initial temperature of the metal right before I put it in my styrofoam cup with water? And if it helps, I can remind you of that step in the procedure that's going to occur. The student boils water, that's why you have ring stands with water there, puts the metal in the water, and then eventually takes it out and puts it in the styrofoam cup. So what's the temperature of the metal right before it gets put into the styrofoam cup? 100 degrees Celsius, the same as boiling water. So that's not a measurement we have to make because we know the temperature water boils at. That right there, that initial temperature of water is the number one thing that students screw up on when we do the calculation section. This is going to give us a negative value. 64.3.
Yep.
And now it's a matter of algebra. I have a variable. I need to divide both sides by 75. I need to divide both sides by negative 64.3. And I actually already have the answer for this, so to save you a little calculation, it's 1.43 And the unit for heat capacity is always the same. It's a joule per gram degree Celsius. What that unit represents is how much energy is needed to make 1 gram of that substance increase its temperature. Metals have a low heat capacity. That's why they feel cold to the touch even though they're at room temperature. Remember last semester you grabbed the desk leg? That feels colder than the desktop even though they're all at the same temperature. It's because it has a lower value. So when you do your calculations for the lab, since you're doing this with a metal, hopefully it's a low value. One more thing I want to bring up with the calculation part before we're kind of done with this. Some students, they don't cancel out the two negatives. Take a negative divided by a negative and makes it positive, and they end up with something that has a negative heat capacity. You can never have something with a negative heat capacity, because what that means is if you heat it up, its temperature actually will decrease. And if you can find something that you can heat up and make its temperature decrease, you have solved air conditioning problems throughout the world. If you can find something that can do the exact opposite, that you cool it down and its temperature increases, boy, you've solved the heating problems throughout the world. So there's no such thing as a negative C value. It would defy the laws of the conservation of energy. And yet sometimes students just forget to do those two parts, so it just doesn't make sense.